models and analyses to climate, carbon, and energy issues. And I'm in a fortunate position that I think that the way you do the best science is find the best people and let them do what they want to do, and provide them with the resources to do that. And I also think that what you did in the past, I think what's important is your ability to analyze problems, to complete projects. But domain knowledge, I think, a smart person can learn a new domain in a couple of months, so it's not a big deal. So let me just give a few examples of what kind of stuff we've been doing over the last year or so. So this is a project that's Steve Davis. Now, Steve Davis got a law degree, decided he didn't like being a contract lawyer, came back here, got a geosciences degree, studying Miocene river flows using oxygen isotopes and so on. Came to me, said he wanted to do a startup on what is the carbon embodied in different products. And so if we look at this lavalier mic, that there was some fossil fuel extracted out of the ground that was used to make this plastics, but also to transport it to me. There's electricity that went into the store or shipping it to me. And so what was the sort of carbon footprint of this product? And so we got into looking at that, and there really wasn't enough data at the product level, but at the level of countries and economic sectors, you could do this analysis. And so we had one paper coming out in PNAS looking at the supply chain from, say, how much of China's territorial emissions are supporting consumption in the United States. And so now we're tracking that back and more or less answering, well, the fossil fuel that was used to make this product, how much of that came from Australia and how much came from Saudi Arabia, and tracking back the supply chain. And so we can do this kind of maps of extraction. So where is the fuel extracted, and then where is it consumed? And then you can take the production emissions, so where's the CO2 emitted, and then where are the products that are consumed, given those, where were the products consumed, where the product was consumed in one country and manufactured elsewhere with its CO2 emissions showing up somewhere else. And then you can sort of put those two things together and track the flow of embodied carbon from the point of extraction to the point of consumption. To the point of consumption. So just looking at this one here, that if you look at here, this one is Japan. So you can see that Japan's getting 44% of their emissions are coming from oil from the Middle East. Some fraction, or I didn't say 44%, but some fraction, maybe 20% is coming from Australia. If you look at their consumption by where their emissions are produced, 70% of their consumption emissions come from, is emitted in Japan, but some of that is coming from emissions from China. But then you could say, well, of the goods that they're producing, the goods that they're consuming, well, they don't have any fossil energy, so here's where the fossil energy is coming from. So that's, anyway, so part of the point of this is, it's interesting in itself, but secondly, that this is a lawyer geoscientist applying his skills to energy system analysis. Okay, I know you're doing some wedge project here. So one of the things we looked at is what are the climate effects of actually doing 7 wedges? And Long Cow, who's about to speak after me, the green line, the red line is a emission scenario for the next 50 years without 7 wedges. The green line shows what happens if you put 7 wedges of emission reduction in there. And the point is, on the time scale of the half century, 7 wedges has a barely detectable climate influence. And so I think if you're doing your wedge challenge, I don't know exactly what it's doing, the problem is not just getting 7 wedges. It's what do we need to do over the next decades to put us on a trajectory to do even much greater provision of carbon neutral energy or greater emissions in energy demand. And so the challenge of the next 50 years is not just to get the 7 wedges, but to get these wedges using technologies that are going to be scalable well beyond that scale. Because if all you do is get the 7 wedges and you can't scale beyond that, you haven't solved the problem. Other kinds of, just to give you a feeling for other studies, how many minutes do I have? You got to keep me. 9 minutes? Okay, good. So this is okay, when you do land, this is another postdoc work on this. So my strategy is find good people, let them do what they want to do. So here's a question. If you cut down a forest, right, you put carbon into the atmosphere, but also, especially in northern regions, forests are dark and absorb a lot of sunlight. And so if you cut down that forest, you might leave a snowy field behind. And so that snowy field reflects a lot of sunlight back to space. And so, especially in boreal forests, it looks like cutting down forests can actually have a cooling influence in that the change in reflection of sunlight overwhelms the carbon storage. And so we basically, this was an analysis now looking at historical deforestation. Is that also true of real places where real people deforested? And it turns out, so we did an earlier study saying that on average, boreal forest, cutting it down has a net cooling influence. Turns out that real farmers when real farmers trying to convert land from forest to agricultural land, they take a piece of forest that's facing more the sun, that has less snow, that's more biologically productive. So it tends, forested land, the land that was actually converted tends to have less snow and be more productive than mean lands. And so while on average boreal forest has a cooling influence, if you look at the areas of boreal forest that were actually converted, it looks like there's a cooling influence to reforesting even there. And so that's sort of an example where doing sort of a more detailed look gave a different answer from the initial back of envelope calculation, which is, I would just sort of do a little plug for back of envelope calculations that, you know, while we run complicated models, if I can't explain the result to myself on a simple back of envelope calculation, I don't believe it. And so I think that complicated models are good for developing intuition and so on, but you shouldn't just believe the result of a complicated model when it could be a bug or something like that. So another kind of study we did, so this was a guy who I hired as a postdoc who he did a PhD dissertation looking at black carbon aerosols in Caldeira Tunnel, which is on the other side of the bay where it has a lot of trucks coming through it, and black carbon is a major health issue. And he wanted to, but black carbon is also has a climate influence because it absorbs solar radiation and contributes to heating. And so he wanted to get involved in this. He'd never run a climate model before. And I said, no problem. You can learn to run a climate model in a month, especially with Long helping him. And so he did this nice study, which is actually came out recently, where it turns out that with little stoves, say in India, putting out black carbon, it goes into the lower atmosphere. Well, that heats up the lower atmosphere and then makes it convectively unstable because you're having this hot air low to the ground. That hot air low to the ground, first of all, it heats the air low to the ground, but it also, by mixing it, tends to increase the amount of convective activity, so increases the rainfall. Whereas once that carbon gets higher in the atmosphere, now you're heating up the middle of the atmosphere, and so that you're increasing the vertical stability of the atmosphere. And so when black carbon's higher in the atmosphere, it's suppressing convection, it's preventing rainfall. And so low in the atmosphere, it's causing increased rainfall. Higher in the atmosphere, it's suppressing rainfall, but it's still heating. If the black carbon gets all the way up into the stratosphere, well, the black carbon acts to shade it acts almost like you had a satellite in space. It acts to shade the planet and therefore has a cooling influence. And so whether its effect on precipitation and planetary temperature depends on altitude. So, you know, this is another study of just what did, people have suggested that past Mongol invasion, Genghis Khan, that this led to basically that these big events led to you know, these big sort of historical events like the Black Death or Genghis Khan's invasion of China, you know, basically destroyed the societies, allowed forests to regrow that had deforested, and some people claim that that had been responsible for climate events in the past, and we just think that's not right. Okay, this is, you know, just giving a little thing. This is So Long, who was an ocean, basically, but before he came to me, basically studied ocean physics and ocean biogeochemistry, and that since has gotten into more global analysis. And you've sort of heard about this idea of one-time CO2 removal, and this is sort of the kind of thing that might be sort of obvious, especially in retrospect to experts, but not so obvious to to the general public, in that if you look at this yellow line, if you remove atmospheric CO2, all the excess atmospheric CO2 from the atmosphere once, so you just bring it right back to pre-industrial times right now, and just do that as a one-time removal, you only get rid of about half of the equilibrium global warming. And that's because of a few reasons. One is as you take the CO2 out of the atmosphere, CO2 that had been previously absorbed by the ocean and by the land biosphere comes back out. The other thing to recall is that the ocean has absorbed a lot of heat, and so that acts as a big thermal reservoir that keeps the planet hot for a while. And so as a result, a one-time removal of all the excess CO2 in the atmosphere only gets rid of about half of the global warming. And that if you want to really bring the sort of temperatures back to pre-industrial, you then have to sort of basically keep on removing this additional CO2 as it degasses from the ocean and atmosphere, which more or less doubles the amount of CO2 you would need to remove. Maybe I'll do it in this, let me just sort of say it in words and let's not worry about the figures so much. That oddly enough, people had there's a lot of basic climate physics that's poorly understood. For example, I think one of the most remarkable things, I think it was 2009, there was a paper published saying why in steady state for an increased greenhouse forcing land heats up more than ocean. And just the fact that people have been studying climate science for who knows how long, that the idea that land, just that you could have a new result explaining why land heats up more than ocean, you'd think that would be done in the 1960s or 30s or something like that. And so that I think that the field has gone to where everybody's trying to predict what's happening in this valley versus that valley and doing all these detailed projections when the basic physics isn't well understood. And so one of the things that my lab's finding out is that that carbon dioxide itself, it's similar to the black carbon story, suppresses rainfall because it absorbs energy in the middle of the atmosphere. And so if you're absorbing energy in the middle of the atmosphere, you're heating up the middle of the atmosphere. The air becomes less dense. So now you have less dense air sitting on top of more dense air below. You're making things more stable, and that's suppressing convective activity that forms thunderstorms and rainstorms and so on. And so that CO2, just the physics of it in the atmosphere, has impacts on precipitation even before it has any temperature effect. Okay, so there's this idea that you can engineer climate by putting aerosols in the stratosphere. And so one of the questions we address is what would this do for food production? And so David Lobel here, who does models projecting effects of climate change on food, we took his models and applied it to these geoengineering simulations in a climate model. And the model projections are basically, you can say there's all kinds of other risks of doing this, but that most crops either are indifferent to or grow better at higher CO2. Most crops, while they like long growing seasons, don't like to be heat stressed. And so if you can reduce heat stress and while giving things CO2, at least in the models, things grow better. And so at least in the models, several different model simulations, that these sort of geoengineering schemes in the model seem to increase food production.